second part of the time response analysis. In the first part, we analyze something as order of the system, different standard test signals, and generally how to find out a time response. That is the general expression, how to find out the time response. Now in this session we will study analysis of the time response for first order system and second order system, as well as we will find first order system step response and second order system step response. So we will begin with first order step response. So unit step response of a first order system. Now this diagram is the standard form of the or general form of the first order system. Is the closed loop system with forward path transfer function 1 by T of S and unit feedback system. So based on the block reduction technique, this overall transfer function C of S by R of S becomes 1 by 1 plus St. Since the highest power of S in the denominator is 1, it is a first order system. And for this system, we need to find a response when the input is unit step signal. So when the input is a step, R of S is equal to U of S, that is equal to 1 by S for a unit step signal. Now based on the transfer function C of S by R of S equal to 1 by 1 plus St, response in S domain becomes by cross multiplying C of S equal to 1 by St plus 1 into R of S, that is 1 by St plus 1 into 1 by S. But we cannot find C of T directly because Laplace inverse of products is not possible. So we have to modify this. So this we can rewrite as 1 by T into 1 by T divided by S plus 1 by T, and that means 1 by S. So by partial fractions we can simplify the partial fraction coefficient as 1 by S minus 1 by S plus 1 by T. So C of S becomes 1 by S minus 1 by S plus 1 by T. So if we find the inverse Laplace transform of this, then C of T becomes 1 minus e to the power minus t by small t by capital T. So this is the general form of the first order system, and the response is unit step response. Suppose it is a response for step input with a magnitude A, then C of T becomes A into 1 minus e to the power minus t by tau. In the similar way, we can find the response for impulse signal by substituting U of S equal to 1, or ramp response by substituting U of S is equal to 1 by S square here instead of 1 by S square. If it is a parabolic, we can substitute as 1 by S cube, and we can continue in the similar fashion. Now the waveform, if we see, this is the input signal R of T, this is the unit step signal, and we know the expression is C of T is equal to 1 minus e to the power minus small t by capital T. When t equal to small t equal to capital T, this small t equal to capital T, then it becomes 1 minus e to the power minus 1, which is equal to 0.632. When t small t equal to 2t, it is 0.865. If we join these points, we will get a waveform of the response something like this, exponentially increasing. So this is the general form of the first order system, response of the first order system. Next we will see the response of the second order system. Before going to the response, we will study what do you mean by second order system. Now this is the closed loop second order system can be represented like this, with forward path transfer function omega n square divided by s square plus 2 zeta omega ns with unity feedback. So standard form of the overall transfer function of a second order system by using a block reduction technique becomes C of s by R of s is omega n square by s square plus 2 zeta omega ns plus omega n square. So remember this is the standard form of the second order system. Now here is a confusion, what do you mean by omega n? It is the natural frequency of the system. Means natural frequency of the system means it is the inbuilt property of the system. With unexcited state, it will start oscillating. That oscillating frequency, unforced oscillating frequency of the system is called as natural frequency. And zeta, it is called as a damping ratio. So it is the factor by which this sinusoidal oscillation vanishes. It is a factor by which this sinusoidal natural frequency vanishes. The ratio is called, this factor is called as damping ratio. Now, order of the system can be represented in another way. That is, as order of the system is also equal to number of roots obtained by equating denominator polynomial to 0. So in this transfer function, what is the denominator polynomial? S square plus 2 zeta omega ns plus omega n square. So this equation s square plus 2 zeta omega ns plus omega n square equal to 0 is called as characteristic equation. So in this case, it is a characteristic equation. Now, in this, based on this equation, we will get roots. But the roots are depends on zeta value. S square plus omega n square and 2 zeta omega ns. So based on this zeta value, this 2 zeta omega n may be forming a perfect square or a square with different roots, or it may be complex roots or anything. So we will classify the second order system based on these roots. Now, it is second order system can be named as undamped system. The undamped second order system is if zeta equal to 0. Means there is no damping factor. Damping ratio is 0. Then the equation, characteristic equation becomes s square plus omega n square equal to 0. So what are the roots of this s square plus omega n square equal to 0? S square equal to minus omega n square. S is equal to square root of minus omega n square. Means roots are purely imaginary. So when zeta equal to 0 or the roots are purely imaginary, such case the system is called as undamped system. Next is underdamped system. That means in this case zeta lies between 0 to 1. In between 0 to 1, greater than 0 and less than 1. Then the equation remains the same, but this factor 2 zeta omega ns is less than the requirement. That means according to the mathematics, if this value is less than the perfect square value, then it becomes, the roots becomes complex conjugate. So roots here in the undamped case, roots are purely imaginary. Here it is complex conjugate. That means a plus jb and a minus jb are the roots of this underdamped system. Third one is critically damped system. Now critically damped system is when zeta equal to 1. When zeta equal to 1, what happens? The equation s square plus 2 omega ns plus omega n square, which is a perfect square. So in this case, what happens? The roots are real and same. Repeated roots you will get. Two roots are real as well as the same. So if the two roots are real and same, or zeta equal to 1, such a second order system are called as critically damped system. And the fourth one and the last one, overdamped system. That is, if zeta equal greater than 1, then the equation is this one and the roots are real but distinct. You can consider the example of s square plus 4s plus 3. So 4s, 2 zeta omega n is equal to 4, which is greater than omega n square. So if this term is greater than omega n square, then it will have real and distinct roots. If this 2 zeta omega n is less than omega n square, then it will have complex conjugate roots. So now we need to find the response, unit step response for the second order system. So in this 4 different classification, we will study unit step response for underdamped system. Similarly, we can apply for others because the roots are either purely imaginary or real. It's a similar concept. But underdamped case, the roots are complex, which has the real as well as imaginary terms. So, unit step response of underdamped system. So as we know, standard form of the overall transfer function of second order system is C of s by R of s is equal to omega n square by s square plus 2 zeta omega ns plus omega n square. Now, this is not a perfect square. So finding a second order system, inverse Laplace, which is not in a standard form, we cannot find the inverse Laplace transform. So I will rearrange this in such a way that by adding zeta omega n square and subtracting zeta omega n square, so the equation remains the same. So adding zeta omega n whole square and subtracting, adding because to make this as a perfect square. And here one more assumption we will do, omega n square minus zeta omega n whole square, which is equal to omega n square into 1 minus zeta square as omega d square, which is a damping frequency. This is the frequency after effect of damping factor. So I can rewrite this C of s by R of s as omega n square divided by s plus zeta omega n whole square plus omega d square. Now this as a overall transfer function, we will find unit step response. So to find out the unit step response, input signal is unit step signal, that means R of s is equal to 1 by s. So response in time domain is C of s is equal to 1 by s R of s into transfer function. Now to find out the inverse, that is to find the C of t, which is the Laplace inverse of C of s, which is the product of two functions. So we cannot find inverse directly. So we need to represent in a partial fraction form like this: a by s plus bs plus c by s plus zeta omega n whole square plus omega d square. If we simplify this and if we find the partial fraction coefficients a, b and c, then we will get a equal to 1, b equal to minus 1 and c equal to minus 2 zeta omega n. You can find out the partial fraction coefficient by any one of the method. So you will get this as answers. So based on that, this C of S becomes 1 by S minus S plus minus I am taking outside because both are minus 1 and minus 2 zeta omega. So I will take minus outside, S plus 2 zeta omega divided by S plus zeta omega whole square plus omega d square. Now to find out the inverse Laplace transform, this is not a standard of any time domain function. This is not a Laplace transform of standard signal. So if I represent in S plus zeta omega n and omega d separately, then I can write as cos function or a sine function. For that I am simplifying this as S plus 2 zeta omega n, I will write as S plus zeta omega n and zeta omega n. 2 separate and I will separate it. S plus zeta omega n divided by S plus zeta omega n whole square plus omega d whole square. Now we know the Laplace inverse of this, which is equal to e to the power minus zeta omega nt cos omega dt. S plus a divided by S plus a whole square into b plus b square e to the power minus a into cos bt. So here this is once again not in a standard form, because for a sine function it is b by S plus a whole square plus b square, but here zeta omega n is there. So I will multiply with omega d as well as divide by omega d. So I will get 1 by S minus this, I will retaining the same because I can find the inverse Laplace transform of this, but for this I am multiplying and dividing by omega d. So once again by rearranging, omega d I am taking into inside this, and this zeta omega n I will take outside. So zeta omega d is what? Omega n into root of 1 minus zeta square. So omega n gets cancelled and it will remains like this. C of S equal to 1 by S minus S plus zeta omega n divided by S plus zeta omega n whole square plus omega d square minus zeta, that is zeta omega n by omega d becomes zeta by root of 1 minus zeta square into omega d divided by S plus zeta omega n plus omega d square. By taking the inverse Laplace transform, we will get C of t is equal to 1 minus e to the power minus zeta omega nt cos omega dt minus this the constant zeta by root of 1 minus zeta square. Inverse of this is e to the power minus zeta omega nt sin omega dt. Now further it contains 3 terms. So if it is possible, I will reduce it to 2. So if I consider this, I will express this in terms of some other function. That is, if root of 1 minus zeta square, that is the denominator term, is equal to sin theta, then zeta equal to cos theta. Because 1 plus sin square theta is equal to cos square theta. Right? So we will get this. Then by rearranging the above equation, what will happen? E to the power minus zeta, I will take common denominator, so comes here, I can take outside e to the power minus zeta omega nt divided by root of 1 minus zeta square into, what is this? Sin theta cos omega dt plus cos theta sin omega dt. Sin a cos b plus cos a sin b, which is equal to sin a plus b. So I can write C of t as 1 minus e to the power minus zeta omega nt divided by root of 1 minus zeta square into sin omega dt plus theta, where theta is equal to tan inverse of root of 1 minus zeta square divided by zeta. So this is the expression for a underdamped system when input is unit step signal. Suppose it is the step signal with magnitude E. So in this case, C of t becomes entire thing is to be multiplied with E. So if this if step input r of s equal to a by s, that means it is a unit step, it is not a unit step signal, it is a simply step signal with the magnitude a. So in that case c of t is into a. Okay, now what is the waveform? See here, though we have derived the equation for only underdamped system, this is the waveform for all this. Now here this red colored one is for underdamped when zeta is equal to 0.1. This green color is also underdamped and this blue color is also underdamped. But if you see this, as zeta increases means damping factor which vanishes the sinusoidal oscillation natural frequency, means as zeta increases it vanishes very early. So within 10 seconds it is sinusoidal oscillation becomes 0 and it becomes a constant. When zeta is equal to 0.1, nearly 0, then it takes a larger time to vanish the oscillation. Now when zeta equal to 1, no oscillation. This is the critically damped. This is the critically damped system. And this light blue and yellow color is when zeta is equal to 2 and zeta equal to 4. So that is overdamped case. Now what happens if zeta is equal to 0? Zeta equal to 0, that means undamped case. So in that case you will get a pure sine wave without diminishing oscillation. You will get a perfect sine wave. Now this is about the step response of underdamped system. Similarly, you can apply the same concept and you can find the response for critically damped, overdamped as well as undamped system. In the next session, we will concentrate on time domain specification of the response, second order system response. Thank you.